Alright, this video is going to focus on the last unit that we did this year. Again, like I mentioned in the end of last video, it's a hodgepodge of different topics. We're going to talk about solutions, acids and bases, kinetics, which is reaction rates, and equilibrium. This unit has a lot of concepts, so I'm not going to spend a huge amount of time talking about those because we literally just did this, but I will try to explain the math a little bit. Alright, to start with solutions, we started reviewing the types of mixtures that we spoke about earlier in the year. Heterogeneous is a mixture where you can see all the different components. So if we have a glass of, let's say, ice cubes and water, my drawing is atrocious, but you get the idea, that would be a heterogeneous mixture. And we have two types. The first is suspension. This is basically where you have a mixture that separates. Part of it's a liquid, part of it's a solid that will settle to the bottom. Muddy water from like a river would be an example of that. Or like if you go to the sand, if you go to the beach with sand water, things like that. The particulates or the solids are going to settle down in the bottom of a bucket or something of that nature. A colloid is the other type of heterogeneous mixture, and this is kind of hard to describe because it's not a suspension, but it's not a solution because it's not homogeneous, so it's a mixture. It's kind of in between those two. Milk is the best example of this. You can kind of see the particles in there, but you kind of can't. Again, it's in between. Homogeneous is where you can't tell the difference between the different parts. So if I had a glass of salt water, it would look like just a glass of water. The components completely blend together. And in this case, if we have NaCl in here, which is salt, the water would be our solvent, which is what is doing the dissolving. It dissolves a solute, and the solute is what is being dissolved. So that would be the salt. So it's dissolved in a solution. So solute is being dissolved, solvent is what's doing the dissolving. And 90% of the time with our stuff, it's water. Alright, we have a couple different types of solutions that are used to describe the nature of the solute in the solution. The first is unsaturated. That basically means that you can still dissolve solute in it. It's not, it can still hold solute, like I mentioned. Saturated solution is one where you have the maximum amount of solute in that solution. You can't dissolve anymore. If you put more in there, it will crash out a solution or it will settle at the bottom as solids. Supersaturated is essentially where we trick the solution into dissolving more than it can actually hold. Because of this, it's extremely unstable. If you remember from class, I showed the hand warmer. It basically starts out as a solution, but any type of destruction, dropping on the floor, cracking that little silver thing, silver ring, caused it to crash out of solution and solidify. So supersaturated is, again, we trick it to dissolve more than actually it can hold. So it has more solute than a saturated solution. That's important. And it's very, very unstable. And like I said, any type of disruption can cause it to solidify. Alright, solvation, or the process of dissolving. Typically, like solution things will dissolve like. Salt will dissolve in water. However, oil won't dissolve in water because they have different properties. So if something is dissolvable in a solvent, then we say it's soluble. If it's not, we call it insoluble. Kind of makes sense. Alright, so before I go about the factors, let's look at the picture that's on your handout. So if you have a salt crystal, okay, the green ones here are chlorine, the smaller blue-purple ones are sodium. And what's going to happen, the thing that looks like Mickey Mouse here, this is a water. The positive parts, which is going to be the sodium, or the hydrogen, is going to be attracted to the big negative chlorine part. All right, and what it's going to do is all the water is going to surround the chlorine ion, and it's basically going to disrupt the bonds or the interactions between the chlorine and the sodium. So it's going to surround it completely as it's shown here, and it's going to break it off from the crystal and dissolve it in water. The same thing is true for the sodium, except for the negative part, which is the oxygen, is going to be attracted to the positive end. So, and it's going to do the same thing. Again, it's going to surround the ion completely, break it off from the crystal, and have it surrounded. And that's what we mean when it's completely surrounded like this. That's what we mean for it to be dissolved. Now, this happens very quickly in most cases, so it might seem like it's kind of tedious, but actually a very quick process. Alright, so let's talk about how we can affect dissolving. One, you can agitate it. You can stir it, you can shake it. When you do that, you're basically allowing the undissolved solute particles to come into contact with a solvent more often. So it has a higher chance of dissolving. The surface area, if you crush something up, you're going to allow the solute particles to interact more, or more of the solute particles to interact with the solvent. So again, it will increase the dissolving. And then finally, temperature. If you ever made sweet tea at home, you always add the sugar when the tea's hot. Never when it's cold, because it doesn't dissolve. So the higher temperature means you have faster particle movement, and you have more interactions between the solute and the solvent. Alright, now that we've talked about what the types of solutions are and solute, solvent, we can talk about how to describe the amount of solute or the amount of stuff in a solution. And that's basically the amount of stuff in a solution is what we call the concentration. And we have basically 4 ways to describe that. The first is percent by mass or percent by volume. The same idea. If we do percent by mass, it's the mass of the solute divided by the mass of the solution times 100. Volume is the same idea, except for instead of mass, you use volume. So it's the percent volume equals the volume of the solute over the volume of the solution times 100. Now, let's look at an example real quick that's given. What is the percent by mass of baking soda, or sodium bicarbonate, in a solution containing 20 grams dissolved in 600 grams of water? So what you do is you take the 20 grams here, that's your solute, because that's what's being dissolved in the other thing. So when you see dissolved in, the first part is the solute. The second part here, water, which I said before, is your solvent. Again, water most of the time is going to be your solvent. You take your 20 grams, you put that in the numerator, then you have to take the total mass, so 20 plus 600 gives you 620 grams. You divide the two and you multiply by 100. So in this case, you get an answer of 3.2%. So it just basically describes the relationship between how much solute there is compared to the solvent, and we do a percentage of it. So that's the first way to describe the concentration. The next way, and the most common way, is molarity. Now, remember that molarity is big M, and that is going to be moles of solute over liters of solution. So it's basically moles over liters. Alright, so an example here is 100.5 milliliter solution contains 5.1 grams of glucose, C6H12O6. What is the molarity of the solution? The molar mass of glucose is 180.18 grams per mole. Alright, so if our formula says it's grams per liter, or excuse me, moles per liter, we're given grams here, so we've got to convert that to moles. So we're going to divide by the molar mass, so we're going to have 5.1 grams on top. We're going to put that number 180.18 on bottom because we want to get rid of the grams, and remember that the number goes with the grams, and we'll have 1 mole on top. So we divide 5.1 by 180 essentially, and you end up with 0.028 moles. We then put that on the top of our molarity formula, because those are moles. Now we're given milliliters here, and our answer has to be in liters. So remember to go from liters to milliliters, or excuse me, milliliters to liters. You're either dividing by 1,000 or you're moving the decimal 3 to the left. So if we move the decimal 3 to the left, we get basically 0.1 liters. Okay, so we divide the moles by liters, and you end up with 0.28 molar, which is big M. Okay, again, molarity is going to be the most common way that you describe concentration. Because it's such an important thing and something that you do often in a laboratory, is we're going to take one solution and we're going to dilute it, meaning we're going to add some water and we're going to change the concentration, lower it down. And we have a dilution law, which really isn't a law, that relates the molarity and volume of one solution to the molarity and volume of another. So M1 V1 equals M2 V2. And again, in this case, molarity is M and volume is V. Okay, so molarity is M and volume is V. Alright, so let's look at an example. What volume of a 2 molar calcium chloride solution, stock solution, excuse me, would you use to make a 0.5 liter to make, a 0.5 liter of 0.3 molar solution? So we have our M1, which is our 2 molar. Actually, let me clear this off so it'll be a little bit easier to read. So the 2 molars are M1. The V2, our second volume, is the 0.5, and our second molarity is 0.3. So let's plug that on the equation. We do our M1, which is 2. We don't know the V1, so we're going to put X in there. And we have 0.5 times 0.3 for our right side of the equation. So to solve for X, we're going to divide both sides by 2, basically. So we end up with 0.5 times 0.3 divided by 2, and you end up with 0.75 liters. So you need 0.75 liters of the 2 molar solution to make 0.3 molars, basically half a liter of 0.3 molar solution. Again, this helps you relate the molarity and the volume of 2 separate solutions. Alright, the next way to express, and actually the third way to express concentration, is known as molality. This is similar to molarity, but different. Molality is little m, and it's the moles of solute over the kilograms of solvent. Okay, so molarity deals with liters, so big M has liters, little m has kilograms. Alright, and the big difference is that the kilograms is not temperature dependent. Kilograms will not change based on temperature. So we use this often when we talk about colligative properties, which we'll get to in a minute, which deals with the change in temperature and how much stuff that you have. Alrighty, so let's look at an example here. So in the lab, a student needs 45 grams, adds 45 grams of sodium chloride to 100 grams of water. Calculate the molality. Alright, so the first thing I need to do is I need to find the molar mass of NaCl. Okay, again, our formula here is moles of solute over kilograms of solvent. So if we're adding sodium chloride to water, the sodium chloride is your solute, and the water here is your solvent. Okay, so we got to convert your sodium chloride to moles, and to do that we need the molar mass. So we take 23, which is sodium's mass, and about 35, which is chlorine's mass, and you get 58.45, which we found before. Alright, so now we take the 4.5 that they gave us in the equation, and we want to get rid of grams, so we're going to put the grams on the bottom, which is 58.45. We divide the two, and you end up with 0.077 moles. Alright, so that's going to go on top of the molality equation. Now on the bottom, they give us 100 grams. Okay, that's actually not 100, that is 1,000. So let's get rid of that. Alright, so again, the relationship between a kilogram and grams is that there's 1,000 grams in a kilogram. So you can either divide by 1,000, or we can move the decimal 3 to the left. So it becomes 0.1 kilograms. Okay, and that's going to go in the denominator. You divide the two, and you get an answer of 0.77 mole. I think that's how you say it. It's a little m. Alright, now our final way of expressing concentration is known as the mole fraction. And it's essentially what the name implies. You take the moles of a certain compound and you divide by the total moles. And mole fraction is symbolized by X. Okay? So let's look at a example. Determine the mole fraction of nitrogen in a gas mixture containing 0.215 moles of nitrogen, 0.345 moles of oxygen, 0.023 moles of CO2, and 0.014 moles of SO4. So what we want to do is we want to take the 0.215 moles of nitrogen. That's going to go in our numerator because that's the compound we're looking for. And we're going to put the sum of all of those moles on the bottom because that's our total mole. Okay? We divide the two and we end up with 0.36. Now, a couple things about mole fractions. They should never be greater than 1. Okay? They should actually all add up to 1. All right? And there are no units. So it should be less than 1. If we were to calculate the mole fraction of nitrogen, oxygen, carbon dioxide, and SO3, sulfur trioxide, it would all add up to 1. And again, there's no units. All right, so we had 4 ways of expressing concentration, which was the percent by mass, percent by mole, or volume, molarity, molality, and mole fraction. All right, colligative properties. Colligative properties basically describe properties of a solution based on the amount of solute there. Okay, so a couple of things we talked about when we talked about colligative properties. First was an electrolyte versus a non-electrolyte. Electrolyte is something that's going to break apart in water. An example of this could be sodium chloride, calcium chloride, potassium iodine, basically anything that's going to break apart. It's going to break into its ions. A non-electrolyte will not break apart when dissolved in water. So in this case, glucose, which is C6H12O6, that will not break into ions when you put it in water. Pretty much any type of organic molecule is not going to break apart. And like I said, colligative properties describes certain properties of solutions, and it's affected by how many solute particles are there. All right, we're going to talk about 4 different ones. The first is going to be vapor pressure lowering. And again, when we talked in class, I described what vapor pressure was. So if we have a container here, and it's closed, we're going to have a liquid here. Now, even though it's a closed container, you're still going to have little particles above the liquid because there's going to be an exchange between the air above it and the liquid particles. And this particle, the amount of particles above the liquid is known as your vapor pressure. Okay, remember that pressure comes from the amount of times that the particles bounce against the walls, and your vapor pressure is going to be basically the pressure of this vapor above a liquid. Okay, and anytime that you add something to a pure solvent, be it water, alcohol, anything of that nature, you're going to increase the interactions between the solvent and the solute particles compared to just a pure solvent. So if we look at a solution of just water versus a solution with water plus salt, let me put some salt in here. So this is NaCl plus H2O, and this is just H2O. This one here is going to have stronger interactions between the particles versus than just pure water. Okay, and so that's going to affect these properties. Because you have a stronger interaction, it's going to take more energy to break those interactions, so you'll have less vapor above a liquid when you have a solute in it. So therefore, the greater the number of solute particles, the lower the vapor pressure is. Again, you need more energy to break the interactions between the particles to go from a liquid to a gas, so you're going to have less vapor there. So it's going to create a lower pressure. Alright, that's vapor pressure lowering. Boiling point elevation and freezing point depression are very similar ideas. They're just opposite directions. Alright, boiling point elevation basically says when you add something to a pure solvent, you're going to increase the boiling point. Same idea as vapor pressure lowering. there's going to be stronger interactions. So it's going to take more energy to break the interactions to go from a liquid to a gas. So you're going to increase the temperature. All right, and we can actually figure out what that temperature is going to be by the formula of delta TB, which is the change in boiling point, equals some sort of constant, which is Kb. Again, this will be given for each particular compound, times molality. All right, and similar to vapor pressure lowering, the greater the number of particles of solute, the higher the boiling point. Freezing point is the same exact idea, except for it's the opposite direction. The greater the number of solute particles, the lower the freezing point. So it takes more energy to slow down the particles. They have to give off more energy to break the interactions to be into a crystal form. And again, we can use basically the same formula, delta TF equals KFM, to find that difference in freezing temperature. Alright, so let's look at an example. What is the boiling point of a 0.40 mole solution of sucrose in ethanol? The Kb for ethanol is 1.22 degrees Celsius per mole, and the boiling point of ethanol, is 78.5. So, to find the boiling point, okay, the change in the boiling point, we take this Kb here, and we're going to multiply it by the molality. So 1.22 times 0.4 gives us a change of 0.49. Now, because this is boiling point, what you're going to do is to find the new boiling point is you add it to the existing boiling point of the pure solvent, which in this case is ethanol. So we take 78.5 and we add the 0.459, and you get an answer of 79 degrees Celsius. If it was freezing point, you subtract it. So boiling point you add, so let me write that down. Boiling you add, but freezing you subtract. Alright, the last one is osmotic pressure, and basically the greater the number of solute particles, the greater the pressure. And here's why. If you recall from from biology, if you had a container, say this is open, let me clear this. Okay, so if we had a container, we have a tube here, okay, and we have a membrane here, and we have just pure water on the left, but we have salt water on the right. So H2O over here, and then NaCl plus H2O on the right. What's going to happen based on the idea of osmosis is that water's going to move from a high to low concentration. Okay, so high concentration to low concentration. And in this case, it's going to move towards the right. Depending on how much salt you have on the right, the more the water's going to want to move. Because the more salt you have, the less water you have. So therefore, the lower the concentration. Now, when we have this water movement, you're going to have a pressure from above that's going to help equalize out the movement of water. And that's what's known as the osmotic pressure. Okay? Alright. So that concludes basically all of the discussion on solutions. Now let's turn to acid bases. There's not a whole lot to recall on acid bases. Basically, acids are going to be things that have more hydrogen versus hydroxide. There's several properties there that we talked about, that it tastes sour, that it turned blue litmus paper red. A couple examples are vinegar and citrus fruit. A base is going to have more OH versus hydrogen. Just a general definition. It tastes bitter and feels slippery. They turn red litmus paper blue. Some examples are milk and magnesia, baking soda, and Drano. Alright, we actually have two models here that describe acids and bases in different situations. Arrhenius is going to be your more basic one. So Arrhenius said that acids have to have hydrogen. That's it. Bases have to have hydroxides. Again, real basic, very simple, easy to distinguish, but very limited. Bronsted-Lowry expanded this definition and said that an acid will give up a hydrogen to become a hydrogen donor, so it will give up the hydrogen. And the base is going to accept it, so it will receive a hydrogen. Now, based on what happens, we have some terms on the results. Now, something that a lot of kids were having issues with, or a lot of y'all were having issues with, is the idea of a conjugate. So in your brain, I want you to put conjugate equals product. So the conjugate is going to be the product of either an acid or base, and they're opposite. So the conjugate acid is going to be the product of the base, and the conjugate base is going to be the product of the acid. So the conjugate base is what forms when you give up a hydrogen. The conjugate acid is what forms when you receive a hydrogen. So the conjugate acid will receive or accept the hydrogen, and the conjugate base will will result after it donates it. All right. Acids have different acid bases have different strengths, and basically the strength comes from what happens when you put them in water. So a strong acid or a strong base is going to completely break apart when you put it in water. So let's look at HI. So HI, when you put HI into water, which is one of your strong acids, it's all going to break apart. So this list right here is going to be your list of strong acids, which again you need to know. And this list here is your list of strong bases, which you need to know. If it's not on one of those list of strong acids or strong bases, it is considered weak. So if we look at let's say HF, which is a weak acid. Most of the particles in water are going to stay together. However, like one particle and 4, let's say, will break apart. So it partially dissociates or ionizes. Strong acid completely dissociates, so this one here with the HI is strong, the one with HF is weak. And the same idea applies to bases. Alright, and when you have a strong acid and a strong base react, you get a neutralization reaction. You get a salt and water. So this is going to be a strong acid and a strong base. Neutralization only happens when you have strong acid and strong base. Alright, we can measure this strength by pH or POH. Okay? And it's basically the negative log of the for pH is the negative log of the hydrogen concentration, and for POH is the negative log of the hydroxide concentration. And if you look at the scales, okay, so for 7 is kind of considered a middle. For pH, if it's lower than 7, it's acidic. If it's higher than 7, it's basic. Alright? For POH, if it's lower than 7, it's basic, and if it's higher than 7, it's acidic. So they're opposites. Alright, and we can also calculate the hydrogen or the hydroxide concentration based on the pH or POH respectively. And all you do is you take the negative log, or excuse me, you take 10 to the negative pH or POH, depending on which one you want. Now, one thing I can't stress enough is that H concentration, the hydrogen concentration, goes with the pH, and the OH concentration goes with the POH. And you can change between the two because the sum of the pH and the POH is 14. Okay, that's written here. And that's something that's important to remember. You can subtract one from 14 and get the other. Alright, so let's look at an example. Calculate the pH of a solution having a hydroxide concentration of 8.2 times 10 to the negative fifth. Alright, so we find the POH because this is hydrogen or hydroxide concentration. We have to find the POH. And we do that by taking the negative log of that concentration, and you get 4.1. Well, if we want to find the pH, we use this relationship pH plus POH equals 14. We subtract 4.1, and you get 9.91. Or excuse me, 9.9. So that's our pH in this situation. Alright, moving on to reaction rates. Alright, reaction rate basically just describes how fast a reaction goes. And the way that you can actually calculate it, excuse me, is based on the change in concentration over the change, that should actually say change in time, not change in rate, I apologize, is change in concentration over change in time. Now, if it's a reactant, if you're looking at a reactant, because reactants are disappearing or being removed, it's going to be negative. The overall rate equation will be negative. But for product, it will be positive. Alright, so let's look at a reaction. Calculate the average rate, reaction rate of A if the concentration changes from 0.5 to 1 molar in 2 seconds. Alright, again, remember that change is final minus initial. So our final molarity, our final concentration is 1, our initial is 0.5. So we take the difference of those, and our difference in time is 2 seconds. So we take basically 0.5 divided by 2 is 0.25 molar per second. Now, this concentration can be in molarity, it can be in moles, it can be in liters, it can be in various different things. But it's basically anything other than time goes on top. Alright, now, to go along with how fast something reacts, a reaction needs to have two things happen, or substances need to have two things happen in order to react, okay? And that needs to be the correct orientation, which is another word for arrangement, or position, okay? They need to be positioned in the correct manner, and they need to have sufficient energy, okay? What they need, they have to have enough energy to overcome the activation energy. And the activation energy is basically what's required for the reaction to go. Now, how can we affect the rate of the reaction? A couple of ways. One, the nature of the reactant. What type of chemical is it made up of? Certain chemicals are more reactive. So if you have a more reactive chemical, you have a higher rate. Kind of the opposite of that thought is noble gases. Noble gases don't like to react, so they're going to have a really low reaction rate. Concentration is another factor. The more particles you have, the more collisions you can have, and therefore you can have more reactions, so higher rate. Surface area. Similar idea to when we were talking about dissolving. More surface area means more collisions and higher rates, so more interactions. Temperature. Temperature makes the collisions move, or the particles move faster, so you're going to have more collisions, and again, higher rates. And the last thing is a catalyst. This is something that you talked about briefly in biology, but basically a catalyst is something that will lower the activation energy and speed up the reaction. So this guy lowers the activation energy, so it lowers the energy required for the reaction to go. And the other important thing is it is not consumed in a reaction. It's there at the beginning and at the end. So it speeds up the reaction by lowering the activation energy, and it's not consumed. Alright, last idea is equilibrium. And I think this was one that a lot of people had issues with. First thing, a reversible reaction means that if we have A plus B goes to C, that's kind of what we talked about up to now. What's actually happening in reality is that we also have some of C breaking down going back to A and B. And when we have this happening, we get a cycle, and we'll end up with basically a state where the same amount is being how do I say this? A and B are forming C at the same rate that C is breaking down to A and B. So it becomes equilibrium. And you have the same exchange rate between the two, and the concentrations basically become constant. They're not equal, that's different. So we can have 5 on the reactant side, but 10 on the product side, but they will stay as 5 and 10. The exchange rate between the two sides is equal. Alright, so if you look at this picture here, you have I2 and H2 that start out, they start reacting, they form HI, but if you notice here in the equilibrium state, we'll have, let's see, we have 1, 2, 3, 4 I2s, 1, 2, 3, 4 H2s, and 1, 2, 3, 4 HIs. And so that will be the case for everything, all the time, once it reaches equilibrium. Now, it's not always going to stay at equilibrium, all right? These reactions are not isolated, and so some guy named Le Chatelier, came up with this idea that if something happens to the reaction, or the equilibrium, that it's going to shift in a certain direction to go back to equilibrium. It likes equilibrium. Alright, so we have a couple different scenarios. One, if you change the concentration. If we add something. So if we have a generic equation, let me erase this line real quick. We have a generic equation here of A plus B goes to C. Okay, if we add more A, it's going to go the opposite direction. So it's going to go towards C. We're going to want to use up that A to make more C. So it's going to go towards, if you add it to the reactant, it's going to go to the products. If you add it to the products, it's going to go to the reactants. And so if you add something, it's going to go the opposite direction. However, if you remove something, so if we remove C here, A and B are going to react to replace what you remove. So it's going to move in the direction of the side you remove from. So if you remove a product, it's going to shift towards the product. You remove a reactant, it's going to shift towards the reactant. Now temperature. The only difference between temperature and concentration is where these things, we should be able to tell where the heat's going to be placed. Okay, so if we have an exothermic reaction, we're giving off heat, heat will be a product. But if we have an endothermic reaction where we have to add heat, heat will be a reactant. So it should be written in the equation. If not, just know that exothermic is a product, endothermic is a reactant. And you're going to use the same rules I just talked about with concentration for heat. You basically treat it as a reactant or a product. So if you remove heat and it's on the product side, it's going to shift toward the product. If you add heat on the product side, it's going to shift toward the reactants. So if we add heat here, if we remove this guy here, the heat, it will shift towards the product. But if we add heat, it will shift towards the reactant. So the same thing I just said. The one that's different is volume and gas. Or excuse me, volume and pressure. For volume and pressure, we only care about gases. Doesn't matter what else, any other phases I don't care about, we only care about gases. So let's say we have a gas here, and we have two of these, and we have a gas here. Alright, and let's say that A is a solid. I don't know. It doesn't matter if you increase or decrease pressure, the equilibrium is always the same. It's going to shift to the side that has the least number of gas moles. Alright, so if we look here, this one doesn't count. The A doesn't count. B has 1 in front of it, so we'll have 1 mole on that side. Well, heat obviously doesn't have any type of gas moles, and we have 2 in front of the C. So that means we have 2 on the left, or excuse me, 2 on the right, 1 on the left. So it's going to go towards the reactants because it has less moles on that side. Alrighty, I believe that concludes this PowerPoint, or the overall PowerPoint. This is the last unit. Hopefully this is a lot of review, and a lot of this stuff is fresh in your memory.